now we come to the main definition of the first half of the course, which is the notion of a group. So a binary structure by itself might not be too interesting, but most of the binary structures we encounter have some additional properties. So a group, G, star or asterisk, is a set, G, together with a binary operation. So again, that just means takes two elements of G and gives back some element of G. It could be the same as the elements you started with, such that a whole bunch of properties are satisfied. That asterisk or star or product is associative. That means A star B, that's an element of G. Then you star that with some element C. That's the same as if you do A star, the result of starring B and C. So that's one condition that a group has. Then the second is an identity element in G exists. It's typically called E, but doesn't have to be. Sometimes it's called denote 1 or sometimes 0 as well. We've seen that an identity element, if it exists, is unique. So there's only, even though it says "and" here, there's going to be one, exactly one. The definition of a group says there is at least one, and we know from previous results that there then is exactly one. Okay, the third condition to be a group is that each element of G has what's called an inverse. That means that, so for each element of G, so let's pick an arbitrary element, little lowercase g in G. Then to say it has an inverse, that means that there exists some element, it could be the same as G, but typically it's not, G primed, such that G times G primed is equal to 1, and G primed times G is equal to E. I said 1, I meant to say E, but sometimes I'll interchange them. Okay, and then G primed is normally written G to the negative 1. I'll read this as G inverse. It isn't literally 1 over G in most cases. So here are some simple examples of groups. So the first example is the set of the integers. So that's positive integers, negative integers, and 0. And the binary operation is usual addition. Then the identity element is the number 0, because you add 0 to any number, you get that same number back. Then the inverse, so 5 primed, is the negative of 5. Same, I just chose 5 as an example to make things concrete. Now, a non-example of a group is the integers with multiplication. Now, it does have an identity element, namely 1. 1 times any number is that number. But 5 primed, the inverse of 5, does not exist in this set Z. The inverse under multiplication of 5 would be 1 over 5, the fraction. But that's not an integer, and so Z with the binary operation of multiplication is not a group. Another element that would not have an inverse would be 0. Okay, so let's take the rational numbers, but let's throw away 0. And then let's consider multiplication. And the identity element is still 1. And now we do have inverses. So for example, the inverse of 5 is 1/5. And so while we haven't checked all the axioms, turns out to be the case that the rational numbers throwing out 0 under multiplication do form a group. The multiplication is associative, it has an inverse, it has an identity element. Another example is that of Z5, which again is the number 0, 1 through 3 to 4 as a set, and the operation is addition mod 5. So the identity element is a 0. The inverse of 4, for example, is 1, because 4 plus 1 is 5 in normal arithmetic, but in mod 5 arithmetic, which is what we're doing here, 5 is the same as 0, and so adding to 4, adding 1, gives back the identity element, which makes 1 the inverse of 4. Now let's go back to talking about groups in general. So a simple fact or proposition is that groups have left and right cancellation. What does that mean? that means that if x times y1 equals x times y2, again, I say times, but in practice, this times could be addition or multiplication or other sorts of operations. But anyway, x times y1 equals x times y2, then we can cancel on the left these x's to get y1 equals y2. So that's what left cancellation means, and analogously, right cancellation. Okay, so for the proof is, well, it's simply what you would do in simple algebra. So if you have this condition, x times y1 equals x times y2, then you multiply on the left by the inverse. So that's, I've been denoting x primed. Eventually, we'll just start denoting it x to the minus 1. But for now, we're going to go with x primed. And then because multiplication or this star operation is associative, that's one of the axioms of being a group, then x prime times x is equal to the identity element. Similarly, here is the identity element. The identity element times y1 is y1. That's the definition of being an identity element, and likewise for y2. So we get y1 equals y2, which is the conclusion. The proof for right cancellation is very similar. You multiply on the right by x primed. Here's a follow-up fact, or theorem, is that if a and b are elements of a group G, then the equation a times x equals b has exactly one solution. And the proof is much like you would do in simple algebra. So suppose we start with this equation and we want to find what x is. We would basically divide by a, divide both sides by a is what you would do in regular high school algebra. Let's do the analogous thing in this abstract setting of an abstract group, and that's multiply on the left by the inverse of a for this operation. So we've been denoting the inverse a primed, so multiply on the left both sides of the equation by a primed. So then because this asterisk operation is associative, asterisk times a is the identity element as well, and doing the simplifications, we get that x is equal to a primed asterisk b, and so we get a solution, and we need to show that there's exactly one solution though. We've shown that there's one solution, but we haven't shown, first of all, that inverses are unique yet. Now we show that there is exactly one solution. So suppose x1 and x2 were two solutions, and we'll show that they're equal. So suppose that, again, x1 being a solution means that a times x1 equals b, x2 being a solution means that a times x2 equals b, and then what that means is, well, because both of these are equal to b, that means a times x1 equals a times x2, and then we know that we can cancel on the left by a, so we get the x1 equals x2, so that there's exactly one solution. We've shown that there is a solution and that there is now exactly one. Next, moving on to this theorem, are that inverses are unique. So the proof goes as follows. Suppose a primed and a double primed are two inverses of an element a. So what does that mean? Well, that means a prime times a is the identity element, and a double prime times a is also the identity element. That's the definition of an inverse of a. And so because these two are both the identity element, they have to be equal to each other, and then by right cancellation, we can cancel the a's and get the a primed has to equal a double primed. Okay, now another theorem is that the inverse of a times b is not the inverse of a times the inverse of b, but rather you have to flip the order. It's b inverse times a inverse. So in words, the inverse of ab is the inverse of b times the inverse of a. This is going to reflect an important property about groups, is that they do not have to be commutative. They can be commutative and often are, but they don't have to be commutative. By commutative, I mean a times b is equal to b times a. Again, that does not have to hold. Okay, so the proof is quite simple once we're given this result, namely to verify that b prime times a prime is an inverse of a times b. Well, we just have to multiply it by a times b and check that we get the identity element. So again, we have to check that a star b times the alleged inverse, namely b prime times a primed, is the identity element, and then vice versa, when you switch the order, b prime times a primed multiplied by A times B is the identity element. And because the multiplication is associative, and again, when I say multiplication, I mean any mean this operation asterisk or star. It could in practice be addition or something else. Anyway, because multiplication is associative, we can drop the parentheses essentially, or redo the parentheses like so, more precisely. And then basically, after a few steps, you get B times B primed, which multiplies to E, and then the E kind of disappears because E times A primed is A primed by the fact that E is the identity element, and then A times A primed is E because of the definition of what inverse is, and that A primed is an inverse. Okay, so then we do indeed get this side of the equation when we start from the left, and this calculation here is similar.